Welcome to this new video on direct displacement based design. With this video we are actually entering into the designing structures through performance based design. This direct displacement based design has been developed over about 30 years, and recently it has been applied to different types of buildings like frame RC buildings, RC shear wall buildings, and so on. So in this video we shall be actually trying to understand the theoretical background of this process, the direct displacement based design. So this will be abbreviated as DDBD. We shall be using this term DDBD again and again in our videos. What is the meaning of this DDBD method? How it is defined? A definition has been given by Priestley et al. It is like this: DDBD is a method of designing to achieve, rather than be bounded by, displacement limits that could be strain based or could drift limit based. So what does it mean? Let us try to follow the meaning of this. So we wish to achieve some displacement rather than be bounded by that as given in code. Code gives actually some limits of, say, drift or strain, something like that. So those are the bounds. But how to achieve this is not given in the code. So in this method we shall be trying to achieve that limits. One is strain based. Generally it is used in the bridge design, and drift limit based. The drift is the interstory drift, usually used for buildings and other structures. This tells how one level is getting drifted from the other level, immediately other level, so that its effect is felt by the users. That effect is minimized by reducing the amount of drift. So we can set a amount of drift in the beginning of design of the building, and we shall try to reach the target through the engineering process of DDBD. DDBD requires conversion of multiple degree of freedom structure to an equivalent single degree of freedom structure. This is very important, and in this video we shall be seeing how the conversion is done. Being a displacement based design, we need to use displacement spectra at various dampings corresponding to the design spectrum. Now we will find the meaning of my previous video on displacement spectra, how it is constructed, what is the use. Some of my research scholars told I am putting too much energy in different theoretical aspects while I am not going to the practical design. So those theoretical aspects are actually necessary to go to the design, so that when I tell a terminology it is clear and you follow it exactly. So this displacement spectra has been discussed in a separate video, you can see in the previous videos. And a typical displacement spectra is shown here. Its x-axis is the time periods of the structure, and y-axis is the spectral displacement in meter. And this has been derived from the design spectrum, acceleration design spectrum of the code. And what has been done here, that acceleration design spectrum has been converted to displacement spectra as per the procedure for various dampings. Because any building or any structure you are designing, it will have its corresponding damping as calculated through the engineering process, and you have to fit that particular curve for that structure and read the spectral displacement for the structure and find out the corresponding time period. It is a reverse process of that given in the code as force-based design. In the force-based design, from the time period you get the force, the acceleration value SA by G. Here from the spectral displacement you get the time period. So this development is historically is like this. Moyle in 1992 gave a rudimentary direct displacement based design method. Then Priestley in 1993 gave another process which he improved over years, 2000, 2003, 2007. 2007 is actually his book Displacement Based Design, Displacement Based Seismic Design. That book is available in the market. Zhu in 2001 and 2003, Pettinga and Priestley in 2005 gave a DDBD method for RC frame buildings. This we shall be discussing in our coming video. Then Sullivan et al. In 2005-2006 two papers gave the DDBD method for RC dual systems or frame shear wall buildings. Sullivan and Lago in 2012 gave the DDBD method for RC frame buildings with fluid viscous dampers. So out of this, and then Moradpur and Dhayastan in 2019 applied the DDBD method for steel frame building with fluid viscous damper. Actually they shown how to optimize the things. Out of this we shall be particularly discussing the Spettinger and Priestley method, Sullivan et al. Method for dual system, and Sullivan and Lago method later on. So we discussed about the equivalent single degree of freedom system. The multiple degree of freedom system is to be converted to an equivalent single degree of freedom system, and we have to find out the properties of this ESDOF system. So here a multiple degree of freedom system exists. A building is shown. It is a 3D system. So at every joint you have 6 degrees of freedom, and you have so many joints about the whole building, and so there will be so many degrees of freedom. This is your multiple degree of freedom system. The masses are supposed to be lumped or located at the floor level. So at the first floor level, one mass, then second mass, third mass, fourth mass, and so on. Though masses are distributed in all the parts, but for the sake of simplicity in design, we consider them to be located at the floor levels. So this whole MDOF system is to be converted to a single degree of freedom system, having a single mass, having a single stiffness, having a single height. This is your ESDOF system. What are the properties it has? It has the equivalent mass ME, it has the equivalent stiffness KE, it has the equivalent height HE, and if it is allowed to have a drift theta d, this is also called design drift. The drift can be measured either in percentage or in radian. Suppose we have a 2% drift, then it is in percentage, it is equivalent to 0.02 radian. So if your design drift is given as theta d, then the movement it is suffering linearly at the top is delta d is a design displacement. This is also called target displacement. So the relationship is very simple, delta d equal to HE into theta d. If I can find out the effective height, then I can find out what is the design displacement. So now how to find this effective mass, effective height, effective stiffness, and the design displacement delta d. This also we shall be writing as equivalent displacement. So we have ME, the equivalent mass, is one property, KE, the equivalent stiffness, another property, and HE, the equivalent height. The equivalent displacement can be written as either delta E, equivalent displacement, or can be written as delta D, the design displacement. We shall be looking to this in coming slide, what is design displacement. So let us find out what is the equivalent mass. We have considered a multiple degree of freedom system. We have taken a stick model actually, having a single column here at different heights. We have the masses M1, M2 and M3, and there the lateral displacement of the mass from the original static position is delta 1, delta 2, delta 3. These are the drift at that story. If you subtract one drift from the other, suppose I take delta 3 by delta 3 minus delta 2, then I get the differential drift between the two floors, third floor and second floor. If I divide it by the height of the floor between these two, height of the story, then I get the drift in ratio, and multiplying by 100 I can get the drift in percentage. So this is a multiple degree freedom system having masses M1, M2, M3, and we want to find a single mass for the equivalent single degree freedom system. The mass is say ME, and the displacement, the effective mass has suffered from the original position is delta E, and the height, effective height is HE given here. So we are interested in finding effective mass ME. In a very simplistic way, effective mass will be that mass which will be producing a water turning moment ME into HE multiplied by, of course, the acceleration, because m is a mass. If you multiply by acceleration, you get the force. So if I multiply the acceleration me and he, I get a overturning moment here at the base of the equivalent single degree of freedom system. The moment, overturning moment in the real building will be similarly mass into m3 into acceleration into this height, m2 into acceleration into the height of the mass 2, and so on, all the masses, all the heights together. That overturning moment of the real building should be equal to the overturning moment of the equivalent single degree of freedom system. So we are designating those masses m1, m2 and 3 say mi, and those distances delta 1, delta 2, delta 3 as delta I from the reference particle line. M is the equivalent mass and delta E is the equivalent distance of that mass from the neutral position. N is the number of masses or number of degrees of freedom or the number of floors for the real building. Now I take the first moment of the masses. First moment means the mass into distance. So if I take the sum of the mass, first moment of masses, it becomes summation I equal to 1 to n mi delta I. This is my equation 1. And if I take similarly first moment for the equivalent system, then it is me into delta E. This is equation number 2. First moment of masses of the real building and first moment of masses of the equivalent single degree of freedom should be equal. So I can equate these two and write me delta E equal to summation mi delta I. This is my equation number 3. Now I take this sum of the second moment of masses. That is, I multiply mi delta I by another delta I, so it becomes mi delta I square, and take the summation. So this is the sum of the second moment of all masses, and the second moment of this equivalent single degree of freedom system is mi delta E square. These are my equation number 4 and equation number 5. Now this should be equal. Second moment of masses should be same, so I equate 4 and 5 and I get this expression 6 mi delta I square equal to summation mi delta I square. I am interested in finding the value mi. So mi can be written very easily as mi delta I square divided by mi delta E square, mi delta I whole square divided by mi delta I square, because these expressions I've got in the previous slide, and mi delta I square I've got in the expression 6. So this was in, I think, equation 3 and this is 6. So those equations I'll substitute here to get the value mi. You see here, when I divide this, it becomes mi square delta I square. So after dividing by mi is only left, and delta I square get cancelled. So this is mathematically valid equation, and I put those expressions on equation 3 and 6 here. So putting this, I get mi equal to this. So this is the expression for equivalent mass of the system. So it is summation mi delta I whole square divided by summation mi delta I square. Now let us find the equivalent displacement. So equation 3 was already available with us. From equation 3, delta E can be written as summation mi delta I divided by me, just by reversing the side of the mi, equation 8. And put equation 7 in 8, that is the expression for mi that we derived just in the previous slide, we are putting here. So you get delta E equal to summation mi delta I, and this is the expression for mi derived in the previous slide. So after simplification, you get delta E equal to summation mi delta I square divided by summation mi delta I. It is mathematically valid because the mass terms will get cancelled, and distance terms will square here and first degree here. So finally one displacement will be left out. So we have derived the expression for equivalent distance. This equivalent distance is also known as design displacement. Equivalent displacement is also known as design displacement delta D. Now we want to find the equivalent height of the ESDOF system. So we have taken again this same system having masses m1, m2, m3 at distances delta 1, delta 2, delta 3 from the neutral position, and the heights of the masses are h1, h2 and h3. We have a single degree of freedom system which has mass me, equivalent distance delta E and equivalent height he. So we are interested in finding this value of he. Now look at this expression. Hi is the height of mass mi from the base, is generalized mass. let Ag be the ground acceleration. So ground acceleration will be producing inertia force in the mass, which will be equal to mi Ag. Considering that same ground acceleration is reaching the mass, for the time being, this simplicity is considered. This force is horizontal force because the acceleration, ground acceleration we are considering in design of structures are always invariably the horizontal acceleration. Vertical accelerations are not critical. The work done by this force in undergoing a displacement delta I is given by delta I mi Ag. Mass into acceleration is force, so delta I distance, if you multiply, you get the work done. Now this rotational overturning work done can be considered like this summation of delta I mi Ag, which is there here, and we are multiplying by Hi to put the rotational effect. So this is for the real system, the summation of the overturning effect, and for the equivalent system the overturning effect is given by delta I mi Ag into He. He is the effective height. Now we will apply the principle of virtual work over these equations. We consider that the system undergoes a virtual rotation delta theta, and the virtual work done by the real system and equivalent system should be same. So we can write delta I mi Ag He delta theta equal to delta theta summation I to 1 delta I mi Ag Hi. So from here delta theta will cancel out, and by putting all the expressions I get H equal to this and this by simplification. So H equal to summation delta mi Hi delta I divided by mi delta I, equation number 9. So by this time we have derived all the unknown parameters of the equivalent single degree of freedom system. Delta E or delta D is given by this expression, summation mi delta I square divided by summation mi delta I. Mi is the mass in the ith floor. Equivalent mass is given by summation mi delta I divided by delta D. In the previous slide we had taken a different expression for Me, but if you put this delta D here you get the same expression. So it is easy to remember. I shall remember delta D, and Me can be easily put like this. So expression for Me and expression for equivalent height is mi delta I Hi summation divided by summation mi delta I. Hi is the height of ith floor or mass Mi, and delta is the displacement of the ith floor mass. Now we have taken a pushover curve. So pushover curve is between the roof displacement and base shear in the vertical axis. So initially your pushover curve is straight line because the whole things are elastic. But after some time inelasticity set in, a little away from the first yield we have a point where this nonlinear condition is such that it is very less and it is not threatening the life, and it is acceptable for good buildings. So that we call as immediate occupancy. Immediate occupancy means I can occupy the building immediately after the earthquake without repair. However, away from this we have more damage. We have the point LS, life safety, where the damage is much more but life is not threatened. And at highest damage we have a point here which is collapse prevention CP, where building has not collapsed but the damage is widespread, almost devastating, but building is still standing. So this is collapse prevention point. In between I want to design my building for certain damage. So damage ranges are given here. Discrete point is IO, one damage state, LS is another discrete damage state, CP is another discrete damage state. In between this IO and LS you have the damage control range, and in between LS and CP you have the limited safety range. You can design your building for any damage state. So suppose you decided to design for this damage state here, damage state corresponding to this point A on the horizontal axis. So if you draw a line from the origin to this point, then you get the stiffness, what is called the second stiffness or effective stiffness, Ke. The original stiffness is Ki, initial stiffness, when everything was straight line. So if I know the KE value, then I can reach to this point where I want to design for. This is called performance point or the target design point. And how to obtain this we have discussed while we discussed the pushover curves. The displacement corresponding to the performance point has different names like delta PP, displacement at the performance point, delta D, the design displacement, delta T, the equivalent target displacement, and today we have used another symbol, delta E, the equivalent displacement. All these are same. So you have to design your system for this displacement to get this much damage state. That is the essence of the performance-based seismic design. And how to design this is what we are discussing gradually. Now one term is there, what is the effective time period. The natural frequency of a vibrating system with stiffness K and mass M, we are considering a single degree of freedom system, single mass, is given by omega equal to K by M radian per second. Now omega also equal to twice pi by T, where T is the time period. So from that I can get the time period formula, T equal to twice pi M by K under root. Now we have got the familiarity with effective mass and effective stiffness. Though effective stiffness we have not derived so far. So if I put the effective values here, the corresponding time period is the effective time period. So we have the effective time period equal to twice pi M effective by K effective under root. This we shall be utilizing in our design, practical design we will see. Now if I square up both the sides of this equation, then it becomes T square equal to 4 pi square ME by KE. So from here you can easily get the value of KE. So K equal to 4 pi square ME by TE square. This is the effective stiffness we shall be utilizing again and again in our design. And the design base shear is now equal to KE into delta D. This comes from the definition of the stiffness, K equal to force by displacement, so BB by delta D, or force equal to stiffness into displacement. Our displacement is delta D for design purpose. Our stiffness is KE for the purpose of the equivalent single degree of freedom system. So if I multiply this KE by delta D, I get a force which is my design base shear in the displacement based design. Now in the next video we shall be taking up the real design with this theoretical background developed in this video. It is from Pettinga and Pichlet 2005. The name of the paper is Dynamic Behavior of Reinforced Concrete Frames Designed with Direct Displacement Based Design. J.D. Pettinga and M.J.N. Pichlet. Journal of Earthquake Engineering, Volume 9, Special Issue 2, 2005, and pages also given here. You please try to download this if it is possible or collect it from friends and read it before I publish my next video on actually this type of design using DDBD method of Pettinga and Pichlet. Thank you. So in this video we have visited the theoretical background of DDBD method, the conversion of the MDOF system to equivalent single degree of freedom system, and finding out the various properties of the ESDOF systems which will be utilized in the design of the buildings. Thank you very much for coming up with me up to here. Please subscribe the channel, like and share the videos, put your queries and comments in the comment box. See you again. Thank you.